Right, so the quotient rule looks at the case where y is u divided by v, and u is a function of x, and v is a function of x. Now while you're copying that down, as a side note, I'll just put down here, just as a recap, we know when, for the chain rule, we use this when. In what situation do we use the chain rule? You don't need to be mathematical about it, you can just describe it in your own words. When do you use the chain rule? Morgan?
When you have a fraction which is to the power of something and you want to differentiate it.
Alright, so are you saying when you've got y equals something like that? Yeah? Yeah, something raised to a thing. So in essence what we're saying, it's a function of a function. Okay? Alright, given the bright able mathematicians there, I'm just going to very quickly, guys, you guys as well, Asim's table, can you just quickly look up? If I just very quick, I'm just doing a quick recap. If I say y equals e to the x, we know dy over dx gives us what? When you differentiate e to the x, what do you get? E to the x. It's one of those odd functions where the gradient function is actually the same as the actual function. Okay, we saw that we were doing functions when I showed you this number e. Now, but if I was to change that and I said, well, y equals 2x plus 1, can you give me dy over dx? Well, that's still easy. It's still going to be our chain rule, okay, where I can rewrite this as e to the power of u, where u equals 2x plus 1. And therefore, e to the power of u, if I differentiate it, we still get e to the u. And then differentiate your u with respect to x, u prime, that just gives you 2. So that gives you 2e to the u. Obviously you want to write it in terms of x, so 2e to the power of 2x plus 1. Okay, so that's basically the chain rule. It's a function of a function. Okay? Alright, but we'll come up, we'll do a whole lesson on exponentials of logs and look at logs as well. But that's a side note. Now the other thing is, we also did the product rule. Okay, under what conditions, how does that work then? Product rule. Yes, please. As you wish.
I don't know how to say it.
Alright, y equals what? What times what? Give an example.
Okay, so like u
Yeah.
times v.
Yeah.
Like 1 and 3 differentiated.
Oh, okay, so when you work out dy over dx?
Yeah.
Okay, so you get u prime,
V
yeah,
plus
Yeah.
v prime u.
yeah. Good, okay. So here we've got the product of two functions. Okay. Now over here it's actually a division case. But we could also have written the same thing as y equals u times v to the power minus 1. And therefore use this product rule. And so sometimes you might get a function when you can actually use either, it doesn't really matter. Sometimes it's obviously easier to use the quotient rule. Sometimes you can use either. Sometimes it's better off using the product rule. But I think you become familiar with those cases as and when you meet them. Okay? So that's basically an overview of what we've done so far. Is that okay? Alright. Let's run through an example, and this is like a three-step question. I'll put it in, and here it goes, and we'll do it step by step, okay? But I like this question because it goes through a lot in just one example. So it says differentiate y equals x squared plus divided by 1 plus 2x cubed. Then it says, and let's just read this really carefully, simplify your answer, find the turning points, and then determine their nature. Okay. The y equals u over v. Because u and v are not in the actual question, and we're writing something to the examiner. The examiner's a mathematician. The examiner's going to say, well, what are u and v? So we better be very clear about what u and v are. So u equals x squared, v equals 1 plus 2x cubed. So we've actually specified what u and v are going to be. Now, like I said, when you do the product rule, it's always good to write down, have a little four quadrant sort of box, and write down u prime, v prime explicitly. So that just gives us 2x, and v prime gives us 3 times 2 is 6x squared. Now, the reason why you write them out like so is, as you can imagine, the actual working out will get quite messy as you make all these substitutions. So therefore, our dy of dx equals v u prime take away u v prime divided by v squared. So writing out the formula, just in case if you do make a mistake, the method mark is there, and we'll just substitute our values in. So v is 1 plus 2x all cubed times u prime, which is 2x, take away u, which is x squared, times v prime, which is 6x squared, divided by v squared, which is 1 plus 2x cubed, all squared. Can somebody work out how you can tidy this up to get the answer on the right? So I'll just put this in the final form and see if you can tidy it up. I'll give you a minute to tidy it up and see if you can get this answer on the right. So that question might well have been show that you get 2x1 minus x cubed over 1 plus 2x cubed all squared. Okay, can you see me at the end? I think I need to talk to you about tests as well.
So shouldn't it be 6x cubed?
Check.
Sorry, 3x.
Whereabouts?
In the bracket on the top, 2x for the final one. No. 2x1 minus, shouldn't it be 3x cubed?
The final one in red,
Yeah.
2x1 minus x cubed over 1. No, that's correct.
6x squared minus x squared is 6x to the 4. Yeah. So you get 2x plus 4x to the 4 minus 6x to the 4. 2x minus 2x to the 4.
Is that okay?
Yeah.
Alright, before I continue, is everyone okay so far?
Yep.
Has everyone managed to go to the final form in red? Hands up if you managed to derive the final red part. Okay, alright, great. Okay. So we've got this part where we sort of simplified it. Now the turning points, let me pick up blue again. My turning point is when dy over dx equals 0. As Ella showed us earlier on, the denominator we don't get involved with. You don't try to solve the denominator because obviously if you do, dividing by 0 will just give you an error and point to some sort of asymptote. So what we want to do is look at the numerator, and if we set 2x equals 0, and we'd also set 1 minus x cubed to be equal to 0. And this obviously just gives us x equals 0, and this gives us x equals 1. Just to save you a bit of time, I'll write the y coordinate as well. So y equals 0 on the top one, and y equals a third. Just to remind you, I'll just write this out. So y equals x 1 plus 2x cubed to the power x squared. So that's the y equation we're looking at. Okay, so there's our turning points. But now the next part is quite interesting. How can we determine their nature? how do we know whether it's a maximum or minimum? Sorry? Right, differentiate it again, that's true. But look at the hassle we've just been through. So with the top part, the numerator, we've got a product, 2x times 1 minus x cubed, so we've got a product there. And then we'll have to apply the quotient. So there's quite a lot of work to be done. Yeah? So the standard is to take a second differential and work out what's going on. But is there another way? David?
We use a point before and after.
Say that again?
We use an x values before and after the ones you have.
Right, excellent. Yeah, so you might, this might actually ring a bell from the C3 coursework. We could use the values before and after, but we've got to pay special attention. We can't just say, if x0 is a root, you can't just pick x equals minus 10, for example, and x equals plus 10, and say, well, is there a sign change? Why not? Sorry?
There might be another bit of a range.
Right, exactly. There might be another root in between, right? So we've got to be careful. So what we would do is probably take something like 1 decimal place away from either side, so maybe 0.9 or 0.1 on either side, okay? And then work out the sign change. Again, just to save the time, I'll just put the little diagram in over here. Okay, so that's what we get. So here we've got x equals 0. Okay, we know the gradient here is 0. There's x equals 1, the gradient there is 0. If we just take a point on either side, let's say it will be minus 0.9, we get a negative. On the other side, 0.1, we get a positive, and therefore it dips. Okay, and therefore this point here will have to be a minimum. And likewise, around x equals 1, on either side it goes up, hits 0, comes back down, and so x equals 1 must be a maximum. Okay, and that tells us the nature of the turning point. Okay, is that okay? Any questions? Okay. Right, we've got about 25 minutes left. What I suggest we do is get on some questions.